So it is my pleasure to introduce somebody who I personally really admire, who I would say there are not many people who are here today as presenters where I can say they literally changed our industry. But this man did. So I would like to introduce Dr. Andrew Cross, who brought us not only the TriCaster, but the industry-changing NDI codec. And he's going to talk to us about pixels and AI and how all this goes together. Take it away, Andrew.
Thank you. So before I get started, I'm really kind of tired of hearing about AI. And I'm going to give a presentation about it. And I hope that this is different. I hope that this is not just another presentation about AI. And hold me to that. You can come up to me at the end and give me a hard time if it is. So, this is my cat. And my cat is called Mochi. And he is going to star in my presentation. So, this is me. And this is my computer. So we, all of us, since we were born, have been told by humans that humans are special somehow, that we do really complicated things that nobody else can do. We get told the world around us is a really complicated place, and it is. And we grew up thinking that, and our whole life we believed that. My cat does not agree. My cat is pretty convinced that I'm useless and that I'm here to serve him. And my computer doesn't really know a whole heck of a lot, to be honest with you. But when you look around you today, everything, and I cannot emphasize this so much, everything we have around us in the world today is software, and created by software, manipulated by software, controlled by software. You know, these chairs were almost certainly designed in a CAD software. The airflow in the AC vents was almost certainly done with computational fluid dynamics in a computer. The building itself was definitely done in CAD. The glass there, like every piece of this, computers played a role in all of it, and humans created all of that software, and it is an unimaginable achievement. If I put up, because we're at a video conference, I put a few pieces of kind of video-ish software that we all use. I use PowerPoint because I'm using PowerPoint here. But if you just took the source code of this software and probably printed it out, it would probably just fully encase this room. There are tens of millions of lines of code in that. And even though they have bugs, you have to realize that the human achievement of handwriting all that and probably only making maybe 0.0001% errors is just crazy. Like, most software doesn't crash all the time. This is a remarkable achievement. But the more remarkable thing is that for all of that brilliance, the tens of thousands of engineers who are so smart working on software, we as computer programmers cannot take, these are 32 by 32 digit grids of handwriting. We can't write software. We do not know how to write software by hand that can tell us what digit that is. That is quite remarkable, actually, when you think about that we can create software that can predict the weather at unimaginable scales. We can't work out how to recognize the most basic handwriting in code. That's remarkable. I don't think many people even truly understand that or probably believe it. So what we do is, as humans, as computer programmers, we actually don't go and solve it directly ourselves. What we do is we take a big blob of math. It's called a neural network, by the way. Take a big blob of math and plug it into a computer and kind of have it work out. And my cat was getting hungry by this point when I was making my slides. And so the way this works is actually really quite understandable. People are going to be talking about AI here all the time and make it sound really complicated. It's not. You take your digits, you feed them into something called a neural network, which is just a whole bunch of nodes. It's going to have a whole bunch of lines between them that are this big blob of math. You train it. Training is just like linear regression that you learned at school. It really is. It's just a fancy version of that. Not very hard. Just drawing a straight line through stuff, except it's probably curvy in practice. And then you train it to give you the digit on output, and this works. This works. And so we rather than programming computers ourselves to understand the digits, we write a program and then train it to solve the digits, and that works pretty well. And it takes a few parameters, and those parameters, which are the numbers we learned, are what's in the network. They represent an understanding somehow of those digits. We don't understand what those parameters actually mean, by the way, but we just know that if you take those parameters, they can turn 32 by 32 icons of numbers into digits. So, my cat was hungry now. And so I gave her food. Him food, I'm sorry. This gives us an idea. This is the next. We knew that you could do this with digits and understand digits, 10, 15 years ago, maybe 20, I don't know, probably not 20. But what we realized next is I have a cat. You know, I can take pictures of cats, not just digits. Like, if I can take digits, why not take pictures of cats? Feed them into a big network, just like I did with the digits. And it goes through and it thinks, and we do this complicated linear regression thing. And this time it's a lot harder because these pictures are color, they're bigger, they're cats, which are difficult to deal with on a good day. And it goes through all of this thinking, goes through all of this thinking. And actually what it does is it puts out a picture of a cat. And this actually works. So you can take pictures of millions of cats, not millions, hundreds of thousands or even tens of thousands of cats, train a network to make pictures of cats, and it produces pictures of cats. And it's not just recalling the ones it's seen. Somehow it learned what a cat is. And this doesn't take just a few parameters. It actually starts to take really a lot of parameters, like millions and millions and millions of parameters that somehow encodes what the essence of a cat is. And this is generative AI. That is all it is. And so don't do this. Right after this presentation, do it. Go to http, thispersondoesnotexist.com, and it is just a website that instead of cats shows people. And I still find it remarkable that you can go to a website and it's showing you pictures that are truly photorealistic of people that just don't exist. They were created by a computer, where what we did is we fed in thousands or tens of thousands of pictures of people. It learned what a person looks like, and it can make totally new people that are just fiction. I find that still remarkable today, even though we all know it's possible. So, this is what everybody is out there talking about right now. You know, it's this basic idea. You take huge data sets, all the language in the human world, all the pictures of cats. You train these huge AI models that are hugely complicated, and they start to behave remarkably like humans do and can do things that humans can do. And I always find it interesting that we're training these things to act like us, and then they're worried about them killing us. That says an awful lot about humans, doesn't it? This, if you have not actually switched the internet on at the moment, is this huge, huge thing at the moment. You know, I just went onto Google Trends and plotted the term AI, and it's increased over what period is that? 2 years, 10x, 1,000%. It's all everybody's talking about. It's all everybody's talking about this presentation. It's all I promised not to talk about and proceeded to talk about. But it is everywhere. Here's a number that I went and worked out that just blows my mind. In the next year, the big tech companies are going to spend $1,000 for every adult in North America on data centers to process AI. In 1 year, $1,000 for every one of you, they're putting that into a data center, and they're almost certainly going to, well, they almost certainly did 800 last year, and they're going to do 1,200 next year. That is how crazy the world has gone about AI. So, my cat has fallen completely asleep at this point. we know that you can take huge data sets, complicated data sets. You can create huge models. Could you take, and how much data would it take to recreate everything? Everything we can see, and by the way, if you can see it, as far as I know, it's real. So if we can take all the data we have and train a really big neural network, it can understand everything. And so let's start thinking through whether this is possible. The first thing you do is you just start with what is a single picture. And this is a single picture right there. And they're made out of pixels. You probably have heard of those before. And every one of those has 3 values associated with it: red, green, and blue. There's 3. Let's assume that our images are about HD. And I'm sorry, I'm a computer scientist, so I use 1024. They're about 1024 by 1024 pixels. Don't ask me why I didn't say 1,000, but they're 1024. And so you take that and you multiply it by red, green, and blue, 3. You end up with about 3.1 million pixels per image. So that's our starting point. That's 3.1 million data points, or pieces of data, or parameters, or what numbers go into a single image. You now take these and you go out and you find every picture in the world of everything that's ever been taken. And if you have done a Google image search, this slide, by the way, took a long time for me to make, but you get the idea. There are millions and millions of images in the world. And so what you can do is you can take all of these images, and let's do the math on this. Every image takes about 3.1 million numbers. And I'm going to assume that we're going to train on about 5 billion images. That's actually not all the images in the world, but it's a good subset. And if you do this, what you're doing is you're training on every picture of water bottles, chairs, ceilings, buildings, people, cats, dogs. And you multiply these 2 together and you end up with a really, really big number. You end up with 15.5 quadrillion pieces of data. And what you do next is really, really simple, except it's not, is you take that 15.5, every image ever seen, and you put it into a network again, just like you did with numbers, just like you did with cats. And it processes, and this time it would take a really long time. Like this takes, you know what? It costs about $500,000 today. It's probably half what it did last year. It takes you a good few months in a big data center. This is a lot harder. And it puts out a picture. And the parameters of that network encode everything we ever seen. And this really works. If any of you have tried image generators before, you can go in and type a picture of almost anything and it generates it. That is how it works. That's the end. But it's not. We've missed the really, really big thing here. Everything I've told you is correct. Everything I've said is you take huge amounts of data and you build these huge complicated models. But somehow, whenever we talk about that, and what everybody here is talking about in every presentation, everything on the internet is talking about, is missed what probably is one of the biggest discoveries of all time. And I truly do mean that. Like, what this means is something that I don't even understand. I left something off that last slide. And what I left off that last slide is how many parameters it actually took. It did take a lot. It took 3.5 billion parameters. That is about what a typical text-to-image model takes. And that is enough to encode pictures that represent everything. That is a representation of our world. That is a representation of architectural ruins and grass and dry grass and everything you can imagine. And so what we did somehow is we took 15.5 quadrillion pieces of data and compacted them down into 3.5 billion parameters. And those sound like big numbers. Watch this next slide super closely, because I'm going to try to represent to you how big those numbers are in relationship to each other. It's gone. This is staggering. For every image of everything we have ever seen, 5 billion images, if you look at the data, the size of the neural network that was required to encode everything, it wouldn't even be 1 pixel on this screen. That blows my mind. That means that with 3.5, and I'm going to give you an idea of how big this number is, which is not very big, I wouldn't even be able to see it amongst the data. Let's do some math on this. It took 3.5 billion parameters to encode everything. Remember, I said it takes about 3.1 million parameters to represent a single image. If you divide one by the other, if people probably already got there, it only takes the equivalent of 1,100 images to be able to encode everything we could ever see. That is not at all expected. 1,129 images is only 18 seconds of video, and what we're saying is, this is what we've found out, is that in the equivalent amount of data of just 18 seconds of video, you could build an image that represents anything we've ever seen. That is not at all expected. I don't know what that means, but it really means something, and I think what it means is this. There is a view of the world that says we can build incredibly complex things with incredibly complex systems, and that is what everybody assumes. Like when you go on the internet and read about large language models, that's the L, large. You're just going to see things about the incredible complexity and how we're training them on trillions of tokens and all this stuff. But how can they end up compacting down to something that is so tiny? And I think that the real answer is that the really big discovery here is not that things are really, really complicated. I think that the big discovery is that actually things are far simpler than we thought. And I think that this is quite remarkable because I actually think that humanity is discovering that because we thought everything was so complex, thought that we were so special, that actually AI is teaching us that that might not be true. And it's not that computers are suddenly doing things that were so difficult for us, but actually that we're finding out that it wasn't that difficult. And I think that that is a really important discovery that potentially is up there with all the other ones that we've made. And I think that we're finding that out now, except because we're humans and believe that we're so special, we tend not to say that. I think this is huge. I'm going to leave with just one slide, this 1129. It blows my mind that with 1,100 images, probably most of you have that many images on your phone, that is enough to encode and build an image of anything in existence that we know of. That's really remarkable. That's all I've got to say.